So good afternoon, everyone, and welcome to the lecture by Professor Reji Philip on the Nobel Prize, the recent Physics Nobel Prize. And my name is Sadik Rangwala. I'm a professor at Raman Research Institute, and I'm here to introduce Reji, who is somebody who actually doesn't require too much introduction in most cases, but I see a lot of youngsters here. So I will tell you a little bit about Professor Reji Philip. So Professor Reji Philip, he did his PhD in nonlinear optics from QSAT. This is in Kerala. And after that, he moved to Regensburg, where he was, where he did a postdoctoral studies. And subsequent to that, he was a visiting scientist at TIFR. And after that, he came to the Raman Institute, and he has been here since. There's literally no better person in the country to talk about these things than Reji, because the work in intense fields and femtosecond lasers, etc., is something that he has been working on for the longest time, and this is a Nobel Prize long in coming, actually. This prize with this configuration of people was expected for maybe at least 15, 20 years. So without taking your time, and Reji's standing between you and Reji, please welcome Reji.
Thanks a lot, Sadik, for those very kind and generous words of introduction. I am very thankful to the Institute and the organizers for asking me to talk to you about Physics Nobel Prize 2023, which was awarded for work in attosecond physics. So the citation says, for experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. So attosecond pulses are the smallest, shortest entities that we have on the Earth at the moment. So these are very, very short pulses of light. Attosecond means 10 to the power minus 18 seconds. So we will compare this with the normal time scales that we usually know in one of the following slides. So these three people were awarded the Nobel Prize: Ferenc Krauss, Anne Lullier, and Pierre Agostini. So we will see what they did for being bestowed with this great honor. The motivation for all this study is to look at things in the time scale, and we have been able to look at things in the time scale from maybe for a few centuries now. And one of the earlier controversies that kind of perhaps accelerated the motivations in this direction was about the trotting horse. So in those days, a lot of horse races, horse carriages, everything was there. So there was a question, somebody asked this question: when the horse is running, is there any moment in time when all the four legs are above the ground? Nobody could answer this very clearly, because that means you need to look at it somehow, and this is too fast to look. So then people developed some better cameras and with faster shutter speeds and all, and finally it was proved that there are moments when all the four legs are actually in air. So this is perhaps one of the earliest use of fast cameras and all that. But then now we are thinking about measuring times of much, much smaller durations. Like, for example, would it be possible to really measure the Bohr orbit time? Of course, it's a classical construct. We know that this is far from the truth, but as a model, it is always good. So the time that the electron takes to orbit around the nucleus in the first energy state, n is equal to 1, is about 152 attoseconds. So this is a very classical calculation. So so we can see that, let's see what kind of a clock we can use for these kind of studies. The stopwatch is good for resolutions like a second. The camera shutter is good for milliseconds. Chemical reactions happen in microseconds. Fast electronics, the fastest, happen in nanoseconds. Molecular vibrations occur in picoseconds. Photosynthesis is very fast actually, femtoseconds. And electron motion in atoms and molecules is in the range of attoseconds. So this is why it is good to have attosecond light pulses, which we can use as clocks for measuring these kind of phenomena. The contents of this talk will be maser and laser, because there is some background for the talk. Q switching is the technique that you need to make nanosecond pulses. Mode locking for making picosecond and femtosecond pulses. High harmonic generation, which is the underlying technique for making attosecond pulses. Isolated attosecond pulses, and finally some applications. I think we all know about the basics of lasers. So essentially the way a laser works is you need population inversion in the system. That means the population of one of the excited states need to be larger than that of the ground state. And then in such a situation, stimulated emission becomes more prominent in the system. And therefore, those photons which are emitted in the stimulated way, they get amplified, and then you get laser emission out of it. So the beam is normally monochromatic and very coherent. So that is the basic characteristic of laser pulses. Laser beams, because we need to make a distinction between continuous wave laser beams and laser pulses, which we will see shortly. The maser was the precursor to the laser. They are now used as timekeeping devices in atomic clocks and as extremely low noise microwave amplifiers in radio telescopes and deep space, spacecraft, communication ground stations and all that. It was invented by Shallow and Towns. So this is Towns with his ammonia maser. Maser is microwave amplification by stimulated emission of radiation. The first laser was actually not invented by Shallow and Towns, even though they were working at Bell Labs in New Jersey on this, a serious study of extending the maser principle to the infrared region. They used to call it optical maser, but then before they could demonstrate, Theodore Maiman from Hughes Research Labs in California, he demonstrated the Ruby laser. Ruby is CR3 plus L2O3. That became the very first working laser in history. So this was the laser he made. So you wanted some kind of a powerful optical excitation. You want to excite your material. So this is what he could get, the best thing. It's a helical flash lamp, which photographers used to use in their cameras in those days. And here is Maiman with the helical flash lamp and the ruby rod. So he kept the ruby rod inside. Now we know this is a very inefficient configuration because most of the light was getting lost in this kind of configuration. The excitation in ruby happened in the blue region and also in the green region, and the emission happened in the red. So from this paper, we actually see the evolution of laser pulses. So what Maiman made was somewhat crude by today's standards, maybe like 100 microseconds pulse width. The pulse width of that laser was essentially the pulse width of, or little less than the pulse width of the flash lamp. However, very soon the technique of Q switching was invented. Then a little later, mod locking was invented, and you can see that the pulse width, if you make laser pulses, the pulse width is actually coming down from 100 microseconds to down, and then things like curl lens mod locking, that gives you like well anything less than 100 femtoseconds. And then finally, this is a regime where we have actually moved from the femtosecond regime to the attosecond regime. So that happens around 1987 when Anne Lullier fires a laser at a noble gas and produces overtones of light. She was not the only person, but she was one of the pioneers in this. And these overtones are what basically the harmonics. In the 1990s, people explore the mechanism behind these harmonics. In 1994, Pierre Agostini begins to develop a pulse measurement technique called rabbit. So, all these, there are very interesting fast pulse measurement techniques by the name frog, spider, rabbit, and all that. So that's the way these are named. So to measure attosecond pulses, that was very, very difficult. You will see that. So this is called rabbit in one of the techniques. Then Agostini produces a train of 250 attosecond pulses. It's a pulse train. It's not an isolated pulse. And then Ferenc Krauss isolates the pulse. He makes a single 650 attosecond pulse. And in the 2000, from 2000 and onwards, the attosecond pulses are used to explore the motion of electrons in various materials. And now in 2023, the Nobel Prize is given. Now this is a nomogram which actually tells us how fast or how short actually are these pulses. Now here we have the age of the universe. This is all in seconds. And somewhere in the middle is the duration of 1 minute. And here you have a 10 femtosecond light pulse. Attosecond is even shorter than that. Now we can see that comparing to 1 minute, how large is the age of the universe. You have to go back in time by the same amount to reach a 10 femtosecond pulse. So it's extremely short, unbelievably short. Now let us see how we make nanosecond pulses. So this technique is called Q switching. What we do here is in a laser cavity, there will be a temporal modulation of the cavity Q factor. So what it means is, this is part of the laser cavity, and I have my laser medium, everything here, and also the other laser mirror, the cavity mirror here, which is not shown. So I excite my laser medium, and then the beam is coming. The stimulated photons are coming this way, and then I have a polarizer in the cavity. So this polarizer will polarize my photons. In other words, it allows only those photons which are polarized along its plane. And then I keep something called a Pockels cell there. This Pockels cell is an electrically activated device which can, which is birefringent when you apply a voltage to it. That is what you learn as double refraction, birefringence. So what it does is, it changes the plane polarized light into circular polarization. And then when it comes back after reflection, there is one more traversal through this. So with that, there is one more 45-degree change, and then that gives you a polarization which is orthogonal to the original polarization. So what happens here is that the beam just won't pass through. As long as you have kept the Pockels cell switched on, you have to give a voltage like 3 kilovolt or something to it. Apply that DC voltage. As long as it is switched on, this is not going to allow amplification of light. It just doesn't allow the movement of photons in there. So what is done is, now you are exciting your system. So remember, we are talking about times in microseconds and nanoseconds. So I have started my flash lamp, which is exciting the system. And the flash lamp is increasing in its intensity. And at some point of time, let's say we call it time t is equal to 0, at that point in time, maximum population inversion has happened. And all this time, I have blocked the cavity by applying a voltage to the Pockels cell. When the inversion is maximum, I just switch it off. So when I switch it off, it becomes just like a piece of glass. So there is no more action from the focal cell, suddenly the cavity will lace. And the cavity will lace at that moment when the population inversion is a maximum. So the result of this is that I get a very strong pulse. I get a giant pulse. People used to call it the giant pulse in those days. And it's extremely short, like nanoseconds. You can get 10 nanoseconds, 8, 5 nanoseconds. That kind of pulses you can get from a Q switching technique. And this is a very standard technique. All the nanosecond lasers which we use, we don't have any microsecond lasers anymore. Pulse lasers start from nanoseconds and then goes shorter. So this technique is not sufficient if you want to make picosecond and femtosecond pulses. So we have to depend on a very different technique called mode locking for this. So for that we need to understand what are the modes. Take any cavity for that matter, put electromagnetic radiation in there, you will have several cavity modes there. So same is the case with a laser cavity also. You have an emitting medium there, which is your laser medium. So there is light in the cavity. And this light is going to be organized in a series of cavity modes. So that is what you see here. In principle, a cavity can contain infinite number of modes. However, it is in reality not infinite because you have a certain gain bandwidth for your emitting medium. So you will have only those cavity modes which are within the emission bandwidth of your system. So you have a certain number of modes like that. And these modes are separated by a frequency interval. Delta nu is equal to C by 2L, where L is the length of the cavity. Now let us see how many frequency modes are there in an optical cavity with a given lasing medium. The first example is that of a helium neon laser. Everybody knows about the helium neon laser. Let us say the length of the cavity is 30 centimeter, and now delta nu is C by 12. That is, adjacent frequencies are separated by delta nu, and that is 0.5 gigahertz. Now the Doppler broadened bandwidth of the helium neon emitting line, that energy level is 1.5 gigahertz. So this corresponds to 0.002 nanometers at 633 nanometer where the helium neon emits. So you can see that the number of lasing modes in the helium neon laser is only 3. It is not more than that. Now compare this with the titanium sapphire laser, which is the one that we use for making femtosecond pulses. There, let's take the same cavity length L. So delta nu is the same, 0.5 gigahertz. However, the bandwidth of the TISAF laser is 128 terahertz compared to the much smaller one of the 1.5 gigahertz of the helium neon laser. And this is 300 nanometer width centered at 800, approximately centered there. In fact, it is from 700 to 1100 nanometer. Very good crystals. It also depends on how good the TISAF crystal, it's a crystal, how good you can make it. When the companies make these crystals, they actually check each and every crystal, and it's an art making crystals. The best crystals will give you fluorescence to a bit extended beyond 100,000 nanometers, whatever. So conservatively, we say 300 nanometer width. So the number of modes you have in that cavity will be 250,000. So that much of difference. So that is the number of frequency modes in a TISAF laser cavity. Now what happens if the phases of all the modes are synchronized? Now in principle, there is no guarantee that the phases of each of these modes are synchronized. However, there are ways in which you can synchronize them. And if you do that, then this is what happens. Because of the phase synchronization, the output of these multiple modes in the cavity will be a series of pulses like this. So that is what you get. And what is important to note is that as the number of modes increases, the width of your pulse will be reduced. So this is the technique by which you generate very, very short pulses. So obviously it means you have to have a medium which has a larger bandwidth. And that is why titanium sapphire, it is, this is, I mean, it dominates the femtosecond market because it has this large bandwidth of 300 nanometers. So this way you make your model of pulses. Now, how do you actually synchronize the phases? There are a few ways to do it. These are called passive mode locking, active mode locking, hybrid mode locking, and all that. So something which is quite popular is Kerr lens mode locking. This is a completely nonlinear optical phenomenon. And here it's also known as self-focusing. So what happens is that in the laser medium itself, in TISAF itself, it is a very good self-focusing medium. When the intensity is higher, of course, for a laser beam, the intensity is naturally higher. But if there is a tendency for the system to lock, that is, if there is a tendency for the phases to lock, then you will have pulses, sharp pulses. They are even more intense. So whenever there is that tendency, the beam will focus, self-focus. Now what you do is you cheat the cavity by putting an aperture there. So now the cavity can have laser action only when you have a shorter pulse in the cavity. So all the other, whenever you don't have really a very good train of sharp pulses, all those things die out, but the moment you have some pulses like that, they will pass through and then they will maintain laser action in the cavity. So this is what happens. And there are ways in which we can assist this process by using acousto-optic modulators and all that. Now this is what we have measured for our own laser, the femtosecond system. What you see here is a train of pulses which come at the rep rate of 82 megahertz. So that is the rep rate at which it works. And they are separated in time by about 13 nanoseconds because each pulse is like 100 femtoseconds wide, and depending on the length of your cavity, we find that the separation, and also because of the 82, all that is dependent with each other. The separation is 13 nanoseconds. But please note one thing: no oscilloscope can measure a 100 femtosecond pulse. Electronics cannot measure it. But what we see here is the separation can be measured. 13 nanoseconds can be measured because for this oscilloscope, the rise time is, it's a normal college level oscilloscope of 100 megahertz bandwidth, but even that has a rise time which is as short as 4.5 nanoseconds. So we can see the separation, but each pulse is, what you measure the width as for 4.5 nanoseconds is actually a 100 femtosecond pulse, which the scope cannot measure.
I don't quite get, why is there a regular,
Huh.
why do you have a periodic set of spikes? You're waiting for something to automatically fall into phase, right, in that medium?
Yeah.
So
Yeah.
why would it automatically fall into phase exactly at the
Yeah,
right
this
time?
is a very interesting question, because what people do, what is found is that if you disturb the cavity, it will automatically fall into place. So the theory of mode locking, the equations actually only tell us the scenario when they are already in phase. But how to make it in phase? In fact, the story is that the very first time the cavity locked was when a screwdriver fell on the table. Yeah. It was running in CW mode, and by mistake from the experimenter, a screwdriver fell on the laser table, and the laser started giving pulses. So, and then they used to call it magic mode locking. So later they realized that applying a disturbance to the cavity, so that's what the AOM also does. The acousto-optic modulator switches the cavity out of alignment for a moment, and then immediately it locks, and once it phase locks, then it will continue. Then we can actually, after that, we can even switch off the acousto-optic modulator. In some cases, what we find, because our laser has both, it's a hybrid system, it has the aperture inside and also the modulator. On good days, less humidity, good power and all that, it locks all by itself. Otherwise, you have to force locking. That's the way it is. So now, having the bandwidth, like I said, TISAF has 300 nanometer bandwidth, but that doesn't ensure automatically the pulse width of, the minimum pulse width. So here we have the idea of the time bandwidth product. So for a given pulse, the product of delta t, that is the temporal width, and the frequency domain with delta nu is called the TBP. And then the theoretical minimum for this, for a Gaussian pulse, is given by delta t delta E is equal to h cross by 2. But that equality, you have to really tune your laser for getting it. If you don't really do that, if you don't tweak your laser, this is often not met, and the pulse width will actually go above. I mean, if you want a 100 femtosecond pulse, if you don't tweak it properly, I mean, you may get a 200, 300 femtosecond pulse there. So what follows the equality in this equation is called a transform limited pulse. As an example, for a temporally Gaussian pulse, the minimum or transform limited pulse duration is given by delta t is equal to we just put the values here, 0.441 by the emission bandwidth. So that gives the minimum of 200 picoseconds for a helium neon laser and 3.4 femtosecond for a TISAF laser. So this is why in the femtosecond laser arena, titanium sapphire rules. I mean, there is no other material which actually people use for making these lasers. Okay, now we have made femtosecond pulses. Why I tell you about femtosecond so much is because all these ideas will be required for attosecond also. To measure the width of these pulses, we cannot measure them using some other device because femtosecond pulses themselves are the shortest events that you can make. So then how do you measure it? You have made something which is already extremely short and there is no faster camera in your hands. So now the only way to do this is to make use of a technique called autocorrelation. You use the same pulse to measure it. So what you do here is you divide the pulse into two parts, and then in this experimental setup, you can see this is the pulse to be measured. So I have a variable delay here, and I have divided it into two using this beam splitter. So these two parts are going through this lens onto a nonlinear optical medium. It is a second harmonic generating crystal. So why I choose a nonlinear optical medium here is because I want to get an effect which is the product of both pulses. So now it is clear, I mean the way this is done, I can apply a delay here, and only when both pulses are together, I get the effect. So when both pulses are exactly coincident in time, I get maximum output of the second harmonic from this. So that is what you see, the maximum output here when the delay is 0 between the two pulses. And the moment I try to go away from there, I can just move a screw and I can move this backward, forward and all that. When I go away from there, the intensity will decrease. Now this is called an autocorrelation trace. And from the autocorrelation trace, I can back calculate the temporal width of my pulse. So this is what is done. That is how we measure the width of femtosecond pulses. Now, there are some issues with femtosecond pulses. They are not like nanosecond pulses. There are a few things that happen when you try to use or when you try to propagate femtosecond pulses through media and all that. So we will see a couple of those things now. One is called self-phase modulation. The pulse will modulate its own phase when it travels through a nonlinear medium, and then the spectrum will get broadened. And this is actually good for some applications. So now let's remember that frequency is nothing but the derivative of the phase of a wave or a pulse. So consider a light pulse propagating free space. So this is Etx is equal to E naught t e to the power I phi, where phi is the phase. And then phi we can write as omega naught t minus k dot x, where k or the propagation vector is given by omega naught by c multiplied by n. The instantaneous frequency omega t is the, I mean we say that Normally for the light, we don't speak about instantaneous frequencies or anything. It is rather constant in time. But anyway, I'm writing it like this. The instantaneous frequency omega t is the time derivative of the phase. So omega t is equal to d by dt of phi t, which is equal to omega naught, which is a constant because n is a time independent constant. The refractive index n is not time dependent for a normal material. So therefore, it is a constant. However, consider a nonlinear optical medium. Let us say it is a third order nonlinear optical medium. For these media, what happens is that n is not exactly a constant. We can write n is equal to n0 plus n2 I, where I is the intensity of the light that you pass through your medium. So I have a nonlinear optical medium here, which is a third order nonlinear medium. I send a light pulse through that, having an intensity I. Now this will modify the refractive index of my medium in this way. Now normally even here I don't write t if I am sending a continuous wave beam, but if I am sending a pulse through it, then it's better that I introduce the time factor there. So I write nt is equal to n0 plus n2 it. The intensity of, because if it's a Gaussian pulse, the intensity increases, decreases like that. So that is it. Now I can write it is equal to I naught e to the power minus t square by tau square for the Gaussian pulse, something like this. So now I put everything back in my original d phi by dt. Now what I get here is that I truly have a change in my frequency now in time. My frequency is not a constant in time, but it changes in time. And it's given by omega naught, which is the central frequency, minus omega naught n2 by cx into d by dt of it. Now, this is the variation of the intensity of the pulse in time, which is large for a femtosecond or picosecond pulse. If I take a nanosecond pulse, it is not as much. If I take a CW beam, it is 0. So we see that when we try to send a femtosecond pulse or a picosecond pulse through a medium, its instantaneous frequency changes. So this is what happens. We have time here, and this is the intensity of the pulse, and the frequency changes like that. Or if you had started with a pulse like this in air or in vacuum, this is what you get after it has passed through your medium. This is called a chirped pulse. The advantage of this, sometimes it is a disadvantage also. The advantage is that this way you can actually modify the frequency content in your pulse. In fact, to the extent that you can generate white light out of it. So now I start with a red pulse or a green pulse or whatever. Usually we start with the red pulse because the titanium sapphire emits at 800 nanometers, which is red. We start with that. I just send it, focus it and send it through water, plain water. That will give me white light because of self-phase modulation. There are also other effects here, like stimulated Raman processes. All that will contribute together to give me the white light. And if I try to disperse it using a simple prism, this is what I get. See, this is the Vignyana, you get white light. So so this is one of the properties of femtosecond pulses, which means you need to be very careful when you are actually sending these light pulses through media. These things can happen. Now, secondly, there is also a temporal broadening of ultra-fast pulses by group velocity dispersion. What happens here is you take the ultra-fast pulse. I'm talking about 100 femtosecond in that range. Anything below that is, these effects will be very prominent. We know that the refractive index of materials varies with the wavelength. So I have my femtosecond pulse. Even a 100 femtosecond pulse has a spectral width of 13 nanometers at 800 nanometer. So that is what I am trying to send through a medium. What will happen here is that the different parts different spectral parts of my light pulse will travel at different speeds through the medium. And imagine a cavity where, this is happening multiple times. The beam is going like that, coming back, going again. So it will make millions of travels through the nonlinear optical medium. And your pulse will get stretched like anything. So this is what we call group velocity dispersion. This is also not really very good for most applications. So what was like this becomes like this. However, fortunately, it's very easy to correct for it in laser systems. You only have to use a pair of prisms for this. Keep it properly, and then you can correct for it. Now, to get some numbers, for optical fibers, that is where this becomes a problem. Think about transatlantic fibers and all, 4,000 miles of optical fiber cable. They still exist. So put a pulse here and try to take it out at the other end. So you need to know how much is the dispersion, how much is the GVT. Typical values are like, 20 picosecond per nanometer kilometer. Per nanometer change within your pulse, when it goes by a kilometer distance, 20 picoseconds is the delay that happens. This is certainly not good. Anyway, in a typical ultra-fast laser layout, all these problems are taken care of. Otherwise, you cannot use them. Now we come to chirped pulse amplification of femtosecond pulses. So this is where the 2018 Nobel Prize was given for Gerard Mourou and Donna Strickland from the university. This work was done at the University of Rochester. And this is actually Donna Strickland's PhD work. So she got the Nobel Prize for that after so many years. And what is done here, what they did, they actually did not invent this technique of chirped pulse amplification. This was already there in the microwave domain. They applied that to the optical domain. So what is done is, the problem was the following. Femtosecond pulses are very, very sharp, and it's like a needle. If you try to amplify that by normal means, which you use for amplifying nanosecond pulses, for example, it will kill your system itself. In that process, your laser will die. So what you should, because of the extreme high intensity. So what they did was, they stretched the pulse in time first. And then you amplify. When you stretch the pulse in time, keeping the energy the same, intensity will go down. The amplitude will go down. So now the energy is spread over a longer time period. For example, in our laser also we do this. When we want to amplify the laser, the 100 femtosecond pulse is expanded to 300 picoseconds, then amplified, and then compressed back again to 100 femtoseconds. So that is what is done here. There are grating stretchers, prism stretchers, compressors, and all that. So it's all used for these things. Okay. So this is the background of the attosecond work. So now we come to what we call the femtosecond barrier. What is this barrier? The titanium sapphire crystal has an emission bandwidth of about 100 terahertz, which can support a mod-locked laser pulse, that is transform limited, of down to 4.5. A little less than that actually. One can go, the very best is 2.7, but let's say 4.5 femtoseconds full width at half maximum, and not less. And no other material has been found which has a larger bandwidth. Now, this is the barrier, this is the problem. So this used to be the limit for quite a while, and nobody could make anything better than this. Naturally, this barrier can be beaten for creating shorter laser pulses or shorter light pulses only by finding a way to generate a series of periodically spaced frequencies which cover a much larger spectral range. 300 nanometers is not sufficient. Now, people found that there are two ways to do this. The first one, and which is mostly used now, is high harmonic generation, and mostly gases are used for this. And the other method is stimulated Raman scattering. I'm sorry for that noise. Noise is not related to what you see on the video. So, okay, what happens here is the following. In the high harmonic generation process, which was predicted in 1992, you take an atom. Now you have, sorry, you take an atom, so it has its own potential there. So that's what, and now its valence electrons are there. They're all in orbit and everything. So now you put your laser pulse there. So that is an optical field. And we know light is nothing but electromagnetic radiation. So it has electrical field and also a magnetic field in that. The electric field, if the intensity is very high, so you have to put in quite a bit of intensity for these phenomena to happen. It has to be at least 10 to the power 14 watts per centimeter square. This is pretty high power. With that kind of power, what will happen is that we know that all atoms have its own Coulombic potential, isn't it? Like there is the nucleus at the center, the electrons are going, in the classical picture, the electrons are going around in orbits and all that. So the electromagnetic force between the nucleus and the electrons is actually very large. For example, if you calculate the electrical potential between the hydrogen nucleus, which is just a proton, and the 1s electron, you see that this is equal to 10 to the power 9 volt per centimeter. So this is equivalent to having a capacitor with two plates separated by 1 centimeter with 10 to the power 9 volts applied to the plates. So you know this is a very, very high field. It's not a small field. However, if you have a laser pulse which has an intensity that is higher than 10 to the power 14 watts per centimeter square, its own potential is something similar or comparable to that of your atomic potential. Now increase your laser pulse intensity a little more, it will overpower the atomic potential. So what will happen here is, see, the atomic potential gets modified by the external potential. If it is 10 times higher, for example, obviously it now takes control of the situation. It's like having a big magnet and a small magnet. You know, the atom is a small magnet here. My laser is a big magnet. So wherever my big magnet is, the small magnet will turn and all that, right? Something similar happens. So what happens now is that the valence electrons find themselves in a very funny situation. They are already in a potential, but this potential is getting modified, and they find that at one point in time, they can just roll out of the atom. Now, this rolling out can happen in many ways. For making high harmonics, we have to precisely control the intensity of our laser pulse. Because if you put in too much intensity, multi-photon ionization will take place. It is not rolling out. The electron will be ejected with a lot of kinetic energy and it will not come back. Here, you give just enough, you modify the potential in such a way that just enough potential variation is there for the electron to roll out. So when it comes out, it has only, the kinetic energy is 0 actually. This is called tunneling. This is a very, very simple classical description of the quantum tunneling of the electron from its atomic nuclear potential. Now, but what happens? You are applying a very large field, and that field will hold the electron in its power, okay? So the field is going up like this, it's 800 nanometer field. It increases, decreases, increases, decreases like that. When that happens, the electron first gets accelerated, but then it passes through the peak, then the field changes direction. So this is called a 3-step process. The first step is tunnel ionization, then motion, that is acceleration, then the field changes direction. So the electron also changes direction. It comes back to the parent nucleus. Now what happens is recollision with the parent atom. Quantum mechanically what is said is that I think, so that's in the next slide. What happened? I think
Or maybe your battery is
no, I think the video did something. Yeah. That's the only video I have. Maybe you have to, oh, you need to connect the power, but that's not why it's stuck. Time? How much time do I have? Almost done? Okay. Oh, I'll do it fast. 10 minutes?
Can you finish the...
Okay. All right. So this is what is called the three-step process. And in this process, when the electron recombines with the parent atom, it generates the high harmonics. That is what happens. And one of the very first experiments of this kind was done by Anne Lullier, and she focused 1 picosecond laser pulses from an ND glass laser to Nobel gas targets, and then at intensities between these values. And she found harmonics up to the 29th in xenon, 57th in argon, 135th in neon, and all that. So you have generated high harmonics in this way. I'll go a little faster now. So basically why Anne Lullier received the Nobel Prize is because she did very fundamental work in multi-photon ionization, in high harmonic generation, and she explained what is called the plateau in high harmonic generation, because so you have a lot of frequencies there, and in the central region it's a plateau more or less. So she explained why that happens, and she used time-dependent Schrodinger, he solved time-dependent Schrodinger equation using what is called the single active electron approximation. She contributed a lot to the full quantum theoretical development of this process. What I told you is a semi-classical phenomenological process. So that is why Anne Lullier was awarded the Nobel Prize. So this is the structure of the high harmonics. You can see the plateau here. And what happens is the harmonic order, this is from 25 to 55, and these harmonics are generated at slightly different times. So this is what she used to explain. She found that out, and she used that to explain the plateau in the system. And then eventually when you have all those harmonics which propagate in a certain phase synchronized manner, very similar to the model locking technique, here also you start getting these pulses. So these are the attosecond pulses here. And the explanation is that there is a continuum component of the electron. When the electron is tunneling out, it is not completely coming out of it. There is a part of the wave function in the atom, and there is another part that goes out. So that is the way it is. So this continuum component of the wave function, it interferes back with the parent part in the atom. And it is in that process, so there is a dipole which is formed in this whole process. It's like one part going out and coming back and all that. There is a dipole oscillation there. And that dipole oscillation is the strongest for a very, very short period at the moment of recombination. And that's a point when high harmonics is generated. And that high harmonics gives you the attosecond pulse train. Now this is her laboratory, part of the lab, and different theses from her group with the titles are there. Now coming to Pier Agostini, his contributions have been, first of all, he was the first person to realize experimental, the above threshold ionization. I'm not going into details of all that. More than that, for this particular work, he invented the principle of rabbit, that is reconstruction of attosecond beating by interference of two photon transitions. That's a mouthful. So what it does is basically it measures the pulse width of attosecond pulses. So this technique is good for measuring the width of trains of attosecond pulses like this. So this is the experimental setup. Here there is argon, a gas, and so another laser is here. So then photoionization. Basically it is photoelectron generation and measuring these photoelectrons. That is the whole idea of all these kind of techniques. So you can see that he has measured these pulses with 250 attoseconds pulse width and with a separation of 1.35 femtoseconds. This is his laboratory, part of it. Then Ferenc Krauss has been in this business for a long, long time, and he is a pioneer in making few cycle laser pulses, then generating broad high harmonic spectra, and he is noted for generating the isolated attosecond pulses. So we were talking about trains of attosecond pulses, but he has really made isolated single attosecond pulses, and measurement of those pulses using cross correlation techniques and other techniques called attostreaking and all that, and a lot of application of these pulses to record electron dynamics in various systems, including biosamples and all that. So to generate isolated attosecond pulses, you need to have very, very short pump pulses, so few cycle pump pulses. There are techniques for that. Here is where the self-phase modulation comes into play. Like you can use hollow optical fibers filled with certain gases for really stretching in the spectral domain, and when your laser pulse is stretched so much in the spectral domain, it is easier to compress it back to very, very short in the time domain. So you get 3 femtosecond pulses and all that. Use them for generating individual attosecond pulses, and then there is also a technique for that. It's called attosecond streak camera. So again, photo electrons are generated, but here a slightly different technique is used compared to the previous technique. So this is part of his lab. Now there is, now you can generate attosecond pulses making use of mostly gases, and they are all the rare gases. So different people have found out different energies they have made, mostly in picojoule, nanojoule range. There is one result of 1.3 microjoule, but everybody in the community knows that it's a wrong result, some calculation error, but it got published. So that is where the situation is. And in 2001 itself, this paper came, Physics at the Attosecond Frontier. Only thing is, in our country, we are a bit slow on these things. Very expensive, by the way, doing this kind of research. So it reads, the abstract is short. Ultra-short laser pulses allow physicists and chemists to watch fast molecular motion as it happens, but many fundamental atomic processes are even faster and require the shortest pulses ever created. So applications, I'll briefly say, attosecond transient absorption spectroscopy. So if you look here, in atomic systems, the way the electrons really, the electrons get absorbed, they get de-excited. So these processes, because they happen in attosecond or fraction of femtosecond time scale, you can use attosecond pulses for measuring these phenomena. So if you look at the x-axis, you can see the delay or your measurement happens in a total time range of 30 femtoseconds using attosecond pulses. So like that, several measurements, charge migration in molecules, you can do that. Look at the time here from 0 to 28 femtoseconds, and you see so many, you have measured very precisely whatever has the dynamics there. Then charge transfer in organic photovoltaic materials. I've just shown just a few experiments. There are others also. So now, one of the latest papers is by Corkum. So he is another pioneer, and many people thought he will get the Nobel Prize, but he did not. So this paper, which came in 2023, actually tells us that, I haven't seen the paper, by the way, but the abstract says, generating high harmonics or attosecond pulses of light is normally thought of as a classical process, because we can explain by classical, semi-classical description. However, a theoretical study has now shown how the process could be driven completely by quantum light. So this is, so a lot of theoretical as well as experimental new things are coming in. There are challenges, because these are not easy experiments at all. So I have listed several possible challenges in setting up, these kind of experiments, but not really going through all of them. So some of the major attosecond research groups are, of course, in Max Planck Institute of Quantum Optics in Garching, MBI Berlin, Imperial College London, ICF of France, Lund University, where and Lulia is from UMIA, King's College London, TUVN, Ohio State. Pierre Agostini is there now. UCF, one of the pioneers is there. Max Planck Center in Pohang in China, it's there. And then there is Extreme Light Infrastructure in the Czech Republic. They have huge, I mean, it's a European facility and really huge systems they have there. So that is what is happening in this area, and thank you very much for your kind attention.
Thank you, Reji, for a lovely talk. You have taken a few seconds, but you have given us a bunch of attoseconds in return.
Thank
So
you.
we are open for questions. Please, yeah.
You showed a plot where they could resolve the attosecond pulses, and the plot I think showed the pulse train.
Yeah.
Is that also done using that delay and the
Pump probe?
Yeah.
Not exactly, not really the traditional pump probe. That kind of pump probe experiment is possible with femtosecond pulses, of course. You are aware of that. But here, what they do, in both those techniques, what they have done is that they have generated photoelectrons and they measure those photoelectrons. That is what they do. But pump probe is possible. Once you have, not for measuring the pulse itself, but once you have the pulses, you can set up pump probe experiments using attosecond pulses. But that itself is a major challenge because how to divide your attosecond pulse is a big problem. Any effort to divide or to use a beam splitter on your attosecond pulse is going to really not only damaging. I mean, it will stretch your pulse and all. Everything is a challenge. Everything is a challenge in this domain.
Yeah, you have two mics. Yeah.
Recently, I don't know, I just wanted to check. I came across some report of zeptosecond.
Septosecond, yeah. I don't know how realistic, I've read about this, but no idea whether these are really happening in the lab. I think it's some experimental report, right?
Yeah.
Septosecond,
10
yes.
to the power minus 21, is it?
Yeah, 18, yeah, 21, yes, 10 to the power minus 21. But not much idea about it to really give you some informed information.
Why, Reji, is it always minus 3, 10 to the minus 12, 10 to the minus 15, 10 to the minus 8?
3 fingers.
Yeah. That's actually a good question. So see, sometimes I think this is more maybe historical or something because even if you just cross the barrier, like let's say from 1 picosecond, even if you go to 900 femtoseconds, you will proclaim to the world that I'm in the femtosecond domain. So that is a kind of chest thumping. I don't know what it is, but truly you are in the femtosecond domain only if you are below 100 femtoseconds, and that is a region where changes are huge. Like from 1 picosecond to 100 femtoseconds is like you can do very similar kind of experiments. But coming down from 100, let's say 50, 35, 20, then this becomes really difficult. You cannot really maintain a laser that is 4.5 femtoseconds. You may have to work on it for hours to even make that pulse stable. So that is, I think commercial offerings are mostly at 20 femtoseconds. Less than that, I doubt whether there are commercial offerings.
Clarification. So you talked about this paper in 2023, which says there's a quantum explanation of this.
Yeah.
But you said, one of the Nobel laureates, Anne Lelier, worked out the quantum mechanics of that, and you
probably what Corkum says is that there are even different kind of explanations or whatever. I haven't seen the paper though. The abstract is so short, So I have to read to really understand what that statement means.
Yeah, yeah.
Lully actually gave a quantum mechanical description.
Yeah, so that's what I
yes.
thought. It's been worked out. So
Yes,
what?
yes.
Okay, maybe
So
something.
what he means, he just says quantum light. So that's the final word. So one has to read. I didn't read yet.
So, Reji, you mentioned that if you pass a femtosecond pulse through water, you get spectrally rodent.
Yes.
Is water then a nonlinear medium?
Third order nonlinear medium. It is tap water. You can use any water.
So, students, how short? Attosecond short? Anybody? Or should I just hand somebody the mic and they have to ask a question then?
I can ask a stupid question. So these are highly specialized conditions in which these happen. Can we imagine some astrophysical conditions or natural conditions where these pulses can be generated?
I doubt it. Okay. No, because these have to be, engineered. Naturally, I mean, in the laser literature, what I understand is that what naturally happens is stimulated emission in some scenarios where the temperature is extremely high.
Yeah.
Apart from that, everything else, even a laser, stimulated emission alone doesn't make a laser. You have to give feedback.
Yeah.
Positive feedback by putting the medium in a cavity. Then it becomes a laser. Otherwise, it doesn't. There are random lasers and all, but that's a different. No, these things we have to engineer. We have to make.
Your temporary broadening is pretty close to pulsar dispersion.
Oh yes, yeah, should be. I mean, I don't know much about it, but there are similarities. Yes, yes.
So, okay, further questions? Okay, while everybody's thinking, I'm going to ask Reji a question. So now we are already at femtoseconds, and as a result, and sub-femtoseconds, as a result, you are in fractions of wavelengths of your
Yeah, the
light. In terms, because if you look at it in terms of wavelength, I know that this is not the picture, but the question is, so let's say you really want to go beyond, let's say you want to get a 1 attosecond, you want to go to 1 attosecond and really time stamp electron motion
right.
in an atom of uranium or whatever it is, so it will be moving really fast.
Right.
So the point is, do you have to move to higher frequencies, like in the X-ray regime and so on and so forth, or are we able to do it in optical?
Certainly not in optical, because in optical the wavelength that we normally use is 800 nanometers, and a single cycle pulse there is about 2.7 femtoseconds. We really don't know what happens to a wave that is not even one full cycle. So for getting something like 250 femtosecond, 250 attosecond pulse, you have to really move to the XUV region. Okay, so like 10 between 10 nanometers to 120 nanometers. That's where all the harmonics are lying. Now, if we want something like 1 attosecond pulse or something, then again we'll have to push into the hard X-ray region.
So is there a theorem that given a certain wavelength, this is the shortest that you can go? Is there some kind of, from electromagnetism, does it just come out through Fourier something or the other?
Yes, absolutely. See, the uncertainty principle is basically the same as the Fourier transform thing.
Yeah, of course.
So therefore, that is the underlying thing here. So if you have this much of bandwidth, then you have this much of, larger bandwidth, shorter pulse.
Okay.
That's it. Yeah.
Continuing on what Sadiq was saying, is basically, is there a ultimate limit, like a fundamental limit from the theory. That
From theory?
yeah, for the shortest possible time scale.
Doesn't look like for the time being. So I don't know whether any other issues will come. Like see, even now, now what we have done in the attosecond domain is just going from the femtosecond domain to the attosecond domain. The change was, rather than using traditional, because if you take titanium sapphire, it is just a I mean, it's a crystal. It is like a dye molecule which emits in a large bandwidth. So dye molecules emit in, in bands. Titanium sapphire emits in a bandwidth of 300 nanometers. Then there was no other material which could be used. There may be materials, but they should be good laser media also for various reasons. Therefore, making a larger bandwidth, you had to invent or find out the technology of high harmonics. Now, within that paradigm, in this high harmonic thing, there is no limitation because it is very similar to the femtosecond situation. Will something else will come, like some other limitation which is very atomic in nature or something? I really don't know at this moment.
Now, just like from quantum mechanics, there's an uncertainty relation,
Yeah. So,
or then relativities, special relativistic effects.
correct.
also
So
come
these
from-
things might kick in at some point of time and then stop our progress there. It is quite likely.
So,
Maybe I'm getting this wrong, but if you take an atom, it's about, say, a picometer in size. I mean, this electron orbit, or what's the?
no,
it's
it's not. So 0.5
Angstroms?
angstroms, yes.
Yeah,
So that's
yeah.
not even picometer, right? But that distance traveled by light, okay. So you have that much. Wouldn't that start becoming a limitation? Because if it was a picometer kind of thing, then you would get into a point that you will spend more time than the time you're measuring for the light to move across, the pulse to move across.
The nucleus will be in picometers,
No,
isn't it?
the nucleus would respond to the light at a different time than the electron, and
Yeah.
so you'd have actually stress build up. Yeah.
No, just
Okay, if there are no further questions, then we still have a couple of things, which is one, can I invite Tarun, our director, to felicitate Reji?
Okay. Thank you so much.
Thank you, Reji, for a lovely talk and all the questions you answered.
Thanks
The
a lot.
other thing is we have high tea for everyone in the ground floor this way. So please go and have a nice meal. Thank you very much.